space switching. When we talk about space switching, it's basically the option to change the parent of a control to set it into a different space, so to speak. So in this case, the rig that we have built up until now, the parent for the hand IK control, for example, is the root control. So before we can add different spaces, we have to add some more controls. So first let's add a simple spine and a simple clavicle module. I already created the empty module groups, so it's the same as the arm and root module layout with the same groups. So first off, let's create the simple spine. We're not going to make an actual functional spine, we're just going to create the controls, and we're going to create a hip, a chest, and a center of mass or center of gravity control. So first let's create 3 locators and call them in the correct way for what they should be. So we have the hip guide, and we have the chest guide, and we have the center of mass of center of gravity guide. And let's place these into the guides group and position them roughly in the place that we want them. Of course, it doesn't really matter because we are going to have them be dynamic, so the position can still change. And now let's change these colors real quickly to the guide colors, and then let's add some controls. So I already prepared these shapes, so that's already done. So let's add these shapes to the node editor, and just the transform nodes, not the shapes. So we can remove the shape nodes, and then for the guides we will remove the shape nodes as well, so that we have the center of mass guide, the hip guide, and the chest guide, and we have the center of mass control, the hip control, and the chest control. And now we're going to do the same as we did for the FK arm. We're going to create the parent offset matrices calculated on the guides of the control and the guides of its parent module. And the parent module in this case for the spine will be the root module. So if we take the spine input parent and input parent guide, and we add them to the graph, and then we add the outputs from the root module, so the main and the main guide, and then we can connect the offset parent matrix of the main output of the root and connect it into the offset parent matrix of the spine parent, like so, and the same for the guide. And now we have connected the inputs of the spine module to the outputs of the root module. We can remove these from the graph, and these are now the parent guide and the parent current matrix of the parent control. So to get the spine control position, we first calculate its offset of its initial position relative to the parent guide. So we make a mult matrix node again, and we take the world matrix of the guide of the center of mass control, so the world matrix, plug it into the first slot, then refresh the inputs, and then multiply the world inverse of its parent guide matrix. So we take the world inversion matrix and plug it into the second slot, and now we have the parent offset matrix, or buffer matrix if you will. So let's rename it. And then we need to add another mult matrix node. And then in the same manner as before, we take the output of the offset or buffer matrix, plug it into the first slot, and then take the current matrix of the root control. So in this case we can take the offset parent matrix because it's a pass-through node. So we take the offset parent matrix plug, because we want to take the input and use it directly as the output, and then plug it into the second port. So now we have multiplied the offset matrix with the world matrix of the control, and then we end up with the current world matrix of the center of mass control. So now we plug the output into the offset parent matrix of the control, and then we have the center of mass control at the correct position, and if we move the guide, we can reposition the center of mass control, and if we move the main control, the center of mass control moves nicely along with it. So now let's rename this to be the world matrix, and then we can proceed with the hip and chest controls. So for this we do exactly the same thing. So we create a mult matrix node, and then we want the hip and the chest controls to move with the center of mass control. So the center of mass control is the parent control for the hip and the chest. So if we want to get the buffer matrix or the parent offset matrix for the hip, for example, we want to multiply the world matrix of the hip guide with the inverse world matrix of the center of mass guide. So let's get those. So then we take the hip guide world matrix, plug it into the first slot, refresh the input ports by pressing 1 and 3, and then we take the world inverse matrix of the center of mass guide and plug it into the second slot. So the world inverse matrix, and now we have the parent offset or buffer matrix. So let's rename it like that. And then we create another mult matrix node. And then we plug in the output of the buffer or parent offset matrix mult node. And then we take the world matrix of the center of mass control, because it's its parent, and we plug it into the second port. And now we have the world matrix of the hip control that moves along with the main control, the root control, and the center of mass control. So let's plug that into the offset parent matrix plug and call this the world matrix. So again, you can see a clear logical setup coming to existence for the controls with the parent offset matrix, mult matrix node, and then the world matrix mult matrix node. And we have to do the exact same thing for the chest control. So let's create another mult matrix node. And then we plug in the world matrix of the chest guide. Refresh the inputs and take again the inverse world matrix of the spine center of mass guide. Plug it into the second port. And now we have the parent offset matrix or buffer matrix calculated, and then we create another mult matrix node, and we plug the offset matrix into the first port, and then we take the world matrix of the center of mass control, because that's its parent, and we plug it into the second plug, and then we plug that into the offset parent matrix of the chest control. And then we name it accordingly. So now we have created the equivalent of the IK controls for the spine, because they are both dependent on the center of mass. For the FK, you would have a chain of controls like you would have in an FK setup. So now the center of mass control moves both the hip and the chest control, and the chest control move individually, and the main control of the root group moves everything. So now that we have this module set up, we can proceed to the clavicle. Well, first let's put the controls in the right group. And then the spine module, as simple as it is for now, is complete. For the clavicle, we're going to do a simple clavicle rig with a start point and an end point that is controlled by a translation control. So let's collapse the spine for now, and then open the clavicle module. So for the clavicle, we're going to need two locators, one for the start position and one for the end position of the clavicle. So let's create these. So left start, guide, and the left clavicle end guide. And let's place these inside the guides group, and maybe let's add another tab to our node editor and add them here. So in the same manner as that we created a oriented guide world matrix for the arms, we're going to create a oriented guide matrix from these guide positions as well. So let's say that the start position of the clavicle would be something like here, and then the end position of the clavicle, well, we could maybe put it somewhere here, and later on we're going to move the arm so it nicely connects with the clavicle, but in this setup it doesn't really matter because we can move the arm at any point in time because the guides are still dynamically creating the arm rig. So we want to create a matrix that is pointing from the start position, the start guide, to the end guide. First, let's recolor the guides. For those who don't know, if you middle mouse press any of the menus, then Maya will execute the last command. So my last command was the color override tool. So if you middle mouse click the menu, it will automatically run that tool again. So in this case, coloring of the guides. So for this, we're going to use an aim matrix, and we want the aim matrix to start at the start guide and then aim with the x-axis towards the end guide, and then with the y-axis point backwards in the world space. So let's create an aim matrix, and then we want the start guide world matrix position to be the input, and then we want the primary alignment to be towards the end guide. So we take the world matrix of the end guide, plug it into the primary target matrix, and then in the aim matrix we want the x-axis to aim towards the end guide, so that's correctly, and then we want the y-axis to align with the world backwards direction, in this case the negative z-axis, so we can just set it to -1 in the z vector, and then because it's the mode is set to align, it's going to interpret this as a vector which is multiplied with a matrix which is just the identity matrix, so it will result in the same vector, so it will be the negative z-axis vector in world space. So if we now create a temporary locator and then we plug the output matrix into the offset parent matrix, we will see that the locator we created points with the x-axis into the direction of the end guide, and then the y-axis is aligned with the world y. So the plane that this creates intersects with the z-axis. Okay, so that's the initial orientation for the clavicle, and we can rename the aim matrix to be the start guide oriented matrix, like so. And what I want to do with this oriented guide matrix is I want to multiply this with its parent matrix of the parent control, so that it moves in space when the rig deforms. And then I wanted to aim at the control that we're also going to move along with the rig. So let's first create the control as well in the right position. So with the end guide, and then let's take the end control, the clavicle control, which I already prepared shape-wise. Let's add it in here as well. And now we can get the relative offset of the guide relative to its parent guide with a mod matrix node. But we didn't connect the inputs of the clavicle yet, so let's add these as well because we need them. These do not have an input. Let's check if our settings are correct. So 1, and do not regraph connected nodes and additive graphing mode. So now we can safely add the input connections, which there are not, so that's correct. Now we can connect the parent guide and the parent input of the clavicle module to the chest control of the spine module, but we did not yet create an output for the spine module. So let's create those as well. So let's create an empty transform node, empty group, and parent it under the spine output group. And then let's call this spine chest output, like so, and spine chest guide output. And add these to the tab where we had the chest or the spine setup. Add them here as outputs. So for the chest out, it's simply just the world matrix of the chest control. So let's take the world matrix of the chest control and plug it into the offset parent matrix of the output for the chest. And the chest input is, or the guide of the chest is just basically the guide. So we can directly plug in the guide world matrix of the chest into the chest guide output, like so. And we didn't reorient the guide in this setup, so we can directly use the guide. So now that we are here, we have the chest and chest guide outputs of the spine, and then we should connect them to the parent and the parent guide input of the clavicle module. So we take the offset parent matrix plug and we plug it into the offset parent matrix plug because we're only using them as pass through. So the same goes here. Take the offset parent matrix of the guide output and plug it into the offset parent matrix of the guide input of the clavicle. So now we have these connected up. We can remove these from the display. And now we have our parent and our parent guide, and we can use that to get the relative offset of the clavicle end guide to its parent guide, and then multiply that with the parent control, so to speak, and then we have the world matrix of the clavicle control. So let's use this one as we have it, the mod matrix. To get the offset or buffer matrix, we take the left end guide control, and then we plug it into the first plug of the mod matrix node, and then we take the world inversion matrix of the parent guide, like so. By the way, if you were to use a script in the end when publishing the rig that removes the output and input nodes, then you would use the offset parent matrix plug it into a inversion matrix node, and then use that output as an input to the mod matrix nodes. But for now we're going to leave it this way. If we in a later stage are going to look at such a script, then we'll take that into account in the script that it does this automatically. So now we have the offset matrix, so let's call this the parent offset matrix. And now let's make another multi-matrix node and plug in the offset matrix or buffer matrix into the first plug, and then take the offset parent matrix of the parent input, which is the control, basically the chest control world matrix, and plug it into the second input of the world matrix, and then rename it to control world matrix. And then we take the matrix sum output of the world matrix node and plug it into the offset parent matrix of the left control for the clavicle. And now you can see that if we move the chest control, that the shoulder nicely moves along with it. And now we can reorient the control to make more sense, like so. So what we now can do, we have now the control which moves along with the rig, but we want the basis of the clavicle, so the oriented guide, we want that as a oriented matrix to move along with the rig as well. So we should do the same thing. We should create a multi matrix node, and we should create the buffer or offset matrix from the oriented guide, so the start, because we have already done the end, which is this basically. And now for the start, we can take the oriented world matrix, the start guide, and then multiply it with the inverse world matrix of its parent. And now we have the start, let's call it the start offset matrix, and then create another multi-matrix node, and then plug in the offset matrix or buffer matrix into the first plug, and then the world matrix of the parent control into the second input. And now we do not have a control for the clavicle start, because we will only create a joint that aims towards the end control and always starts at the start position. So we can just reuse the temporary locator to visualize. So we plug the output of the world matrix node. Let's call this world matrix. Take the output, plug it into the offset parent matrix of the locator, and now let's make this a little bit more clearly visible. If we move the chest control, then the locator, which is representing the clavicle start oriented matrix, and the control for the clavicle moves along. And what we now want to do, because in this rest position, the x-axis nicely aims at the control, and what we now want to do is that when we move this control, the orientation nicely matches the direction of the control. And we can use an aim matrix for that. And if we use an aim matrix where we only align the x-axis, and we do not specify a secondary mode, then Maya is going to calculate the shortest path of rotation via a quaternion rotation. And basically, for example, if you have this locator and we temporarily duplicate it, and then we rotate it like this, if you now look at these axes, basically the x-axis of this locator is going to be aligned with, say, this is the new direction that aims towards the control. Then the shortest angle between these two axes, like the two x-axis, is going to be the rotation. And how this works is that if you take these two vectors, so the x-axis of this locator or matrix and the x-vector of this matrix, if you take the cross product of those, that will generate a perpendicular vector, so a vector that is perpendicular to both these x-axis vectors, and then it's rotated around that axis. So depending on the rotation or direction of the second vector, the axis, the vector where it's rotating around, changes. But this gives the most stable result, because the rotation is always based on the original orientation of the start of the clavicle, and then it takes the shortest rotation that matches the x vector axis with the aim vector. So let's set this up. So we can remove the temporary locator or the secondary temporary locator. So if we now create an aim constraint, aim matrix, sorry, and we take the start world matrix, it feeds into the temporary locator, and set that as the input matrix. So then this matrix is the basis for the aim matrix. And now we plug in the control into the world matrix of the control into the primary matrix, and we set the primary input axis to the x-axis, so it aims with the x-axis and it aims towards the clavicle left control position, and we do not specify a secondary alignment, so it does only the primary alignment. And if we now, for example, look at the output and plug that into the locator, if we now move this, then the locator or the joint later on will nicely follow the clavicle control and align the clavicle with the orientation. And this makes sure that there is as good as no twist in the shoulder and only swing to match the position of the clavicle control. Okay, so let's reset this. And what we now have to do is create a joint for the basis, which has the rotation of the, well, which now is the locator, could be the joint. And then we have to also create the end joint. And for the end joint, we want to have the same orientation as the start, but we want the position to be that from the control, so that it stretches with the control as well. So let's set this up. So let's call this maybe go start. Let's call this one the world matrix and this one the base world matrix, because that's what it is. Like so. And then maybe create a temporary joint, or just create the joint. Let's set the translation to 0. And then plug in the start world matrix into the offset parent matrix of the joint. So now that we have the start joint, and then we can call this clavicle start joint, and then we duplicate this one, and then we call this the left end joint. Now what we want to do is we want to take this matrix and then only take the position of this matrix and then blend it into the end joint. And for this one, let's use the pick matrix, because we're going to use the rotation, scale and shear, and just not the translation. So it's relatively fast to use the pick matrix for this, because only checking out the translate will keep the basis vectors intact and only resets the translation vector. So now we have the rotation matrix, and now we can take the translation of this control and plug it into this matrix. We cannot do that directly in Maya. So what we could do, for example, is use the translate from matrix. We take the world matrix into there, so now we have the translation. And then we could use a 4x4 matrix and plug in the X, Y, and Z into the X, Y, and Z translate positions of the matrix. And then we could use a mult matrix to add these two matrices together, but in this case because we only want to set the translation and leave the rotation intact. It's kind of a waste of resources to do all the multiplications. We can use the add matrix, and then we should set the 3 index, so the W component of the translation vector, to 0, and all the other values to 0 as well, because now it's going to do a piecewise addition. So the value, the x component of the basis vector x will be added to the x value of the basis vector x of the second matrix. So now we can take the output of the big matrix and then add it to the output of the 4x4. And if you now look at these 4 matrices, you can see that these are all 0, including this one, and these all have values, and these should always be 0, and this is 1. So basically it's just going to say, okay, this value gets added by this value, and this value is added by this value, and that's for all the fields will be added. So it's only addition, 16 additions instead of all the multiplications as well. So it saves some computation. And now if we take the output of this and plug it into the end joint, you will see that we now have the joint at the position of the control and nicely oriented to the clavicle control, or the clavicle start. So this way we have the end joint of this setup. And now let's rename these nodes correctly. So I shall do that off screen. So I have renamed them to be clavicle left control out world pos, and the left control out world pos matrix, this one, and then the start world rotation matrix, and the addition is called the end world matrix because it is the world matrix for the end joint. So now we have a setup for the clavicle. We can reset this to its default position, and then we have our clavicle, super simple clavicle setup that we can work with for our space switching. And while we're at it, we can maybe add one more thing to the clavicle setup, because now, of course, when we translate the control, the clavicle stretches and shortens. So we could build in an attribute that prevents the clavicle from getting longer or shorter if the animator wishes so. So to do that, we can take the original length between the guides, because that's the basis length. So let's create a distance in between and add the world matrices of the guides into there. So into the matrix 1, the start guide, and the end guide into the in matrix 2. And now we have the distance. So what we will do is we have the original length, we can calculate the current length, and we can blend between those two lengths and then recalculate the world matrix of the end joint or end output by offsetting the joint from the start joint by setting the translate x value as an offset matrix and multiplying it with the start matrix. So let's do this. So we create another distance between node, and then we take the start world matrix, which is this matrix, which gets moved with the rig, and we put that into the matrix in 1, and then we take the position or the world matrix of the clavicle control, and we plug that into the in matrix 2. So now we have the current length, and the original length, and we can use a blend to adders node to blend between those two. So let's show all attributes so we can see the input. So let's say if we want to enable the locking of the length, we will have an attribute that says enable is 1, and if the attribute blender is 1, it will take the second input. So we will have the current length, the scaled and compressed length as the first input, and we have the original length as the second input. And this is now our blender between the offset in translation between the start and the end. And if we now repurpose the, now let's make a new 4x4 matrix and show all the input attributes. If we take the output of this and plug it into the translate x plug, so the x component of the translation vector of the matrix. And now if we create a multi-matrix node, so we're going to use a multi-matrix node, and we're going to multiply the output of this offset matrix with the world matrix of the start, so this one. So we take the world output matrix of the start world matrix, plug it in, and then we have our new world matrix. So if we plug that into our joint to visualize it, we can see that it doesn't change anything for now. And if we translate our clavicle control, and if we go to the blend adders to node and we set the blend attribute to 1, it can go over 1, so let's set it to 1. Then now you will see that if we move the guide, or sorry, the control, that the clavicle does not change in length. So now we have created a clavicle setup where we can lock the length of the clavicle or make it stretchable. So we should add a attribute on the control for this. So let's add attribute float value. Let's call this lock length. Let's say there's a minimum of 1 and a maximum of 0, and the default is 0. So now we can take the attribute lock length, plug it into the attribute blender, and now we have the possibility to lock the length and unlock the length on the control. So now we can omit these nodes because we have created a new setup that does the same and has the locking of the nodes as well. So we'll remove these ones and rename the nodes correctly. So I have renamed the nodes to be the current length, which was the length between the start and the control, the current length, which was the length between the guides, the start and the end guide, and then the attribute blender I have called the end local TZ because it's the local translate Z of this end matrix, and then the 4x4 matrix is called end local matrix, and the multi-matrix node is called the end world matrix, which produces the matrix that feeds into the joint. So with this we have finished the clavicle rig for real now this time. Let's reorder this a little bit, and then we are going to move forward to the actual space switching. We can remove the temporary locator and clean up a little bit because the control should be in the controls group and the joints should be in the joints group, and then reset the control position and maybe lock and hide some attributes as well. For now, just visibility for these controls, and for the clavicle we're not going to use any of the rotate or scales, so we're going to lock and hide those, visibility as well, and then we're left with what we need. Reset the translation on the clavicle as well. Okay, so now we have our body rig, so to speak, and now we can move our arm to a more logical position. So let's take the arm upper and hand guides and move the arm to a position that makes more sense. for now, let's maybe just put it somewhere here, and the settings guide as well for the arm. Let's put that here. So now we have rearranged the rig to make more sense. There's one more thing we have to check before we proceed, is that if the scaling of the rig still functions for the created modules, and if we now scale, we can sure enough see that the length of the clavicle changes, and that is because we are comparing the original length, which is the length between the guides. We're comparing that with the current length, which is the the length between the scaled rig. So of course the length is then used, also the length that is already longer because of the global scale of the rig, and that is used in a matrix, and which matrix is multiplied by the start world matrix, which, as we can see in the plug, has already the scale of the world matrix. So the scale is applied twice now. So what we have to do to fix this is when we calculate the current length, we have to use the matrices which are not scaled by the world or the root control. So what we can do is the matrices that we use, we can multiply them with the inverser of the main control, the inverser world matrix of main control, so we get the length in the non-scaled rig. So we can use the non-scaled length in the rig so that it gets scaled in the right at the right time. So for this we need a new input to our clavicle, because we now only have the parent and the parent guide. So the same with the arm, we need to use the main and main guide input. We need to add those. So let's add a let's do it here for change. A transform node. It's basically just an empty group, same as pressing Ctrl G in the viewport with nothing selected. And then we move them into the input group of the clavicle. Let's call this in the same manner main input and main guide. We're not going to use the main guide at this point, but I'd like to add them both as well. So with these here, let's then add the let's say the root module outputs. We're going to use these as the inputs for this. So the main output is going to go into the main input of the clavicle, and the main guide output is going into the main guide input of the clavicle. So let's take the offset parent matrix of the main output and plug it into the offset parent matrix of the main input, and the same for the guide. And then we can remove these from the panel. And then now we can use the, let's see where we're here. We can add a multi-matrix node. And we can multiply the output matrix. And we can then multiply it with the inverter world matrix of the input. What we as well could do is we could take the scale from the control and use the scale as a scalar directly on the current length. That would only work if you only use uniform scaling. So if you would scale all axes in the same amount. So if you limit your rig to scale in all axes in the same amount, so you do not support a non-uniform scaling like this, then you can take just one of the scale values of the X, Y, and Z component, because they will be the same, and you can use that to multiply this value here. So it will be less calculations, but for this example I'm going to use the multiplication with the inverser world matrix so that it does support non-uniform scaling of the rig. It's not something that is probably used very often, but for this tutorial series I want to show it this way. So then we take the output of this and plug it into the first matrix plug, And then we do the same thing. We create another mult matrix node. Where we plug in the output of the clavicle control. And then we multiply with the inverse world matrix of the main input as well. And then we take the output and plug that into this. So what you will see now is that if we scale the rig, the scale of the clavicle stays correct. So if we reset this to 1, we can see that it works, and if we rotate it, it works as well, and translating it. Everything keeps working, even if in non-uniform scaling. So let's rename these quickly. So I've renamed them to no main scale start build matrix and the left control no main scale. So now this is done. All that is left to do now is to connect the arm module to the clavicle module, because now the arm does not move with the clavicle yet. So if we go to the arm module and we go to the inputs and we select the parent inputs and we graph the input of them, we can see that they're still connected to the main module. So let's bring in the output for the clavicle, which we have not created yet. So let's create the output of the clavicle first. So go back to our clavicle tab and create an empty transform node. And then for the output, we can use the end world matrix, like so. So this will be our output transform, and now we have to generate the same guide rest matrix. For this, we cannot simply use the end guide because the orientation is different. So what we need to do is we constructed the oriented start guide. So if we create a temporary locator again, and we plug the output matrix into the offset parent matrix, we can see that this is the orientation that we want. We only want it to be at the position of the end. So for this, we can again change the position or multiply this matrix with the length offset. But for now, we can just take the basis vectors of the transform and then swap the translation vector with the translation vector of this guide. So let's do that. And because this is not a runtime node, because the guides are only calculated once, it doesn't really matter how optimized we do this. But for now, just let's use the pick matrix workflow for this one. So we take the matrix, and then we say we only want the rotate, scale, and shear. So we end up with a nullified translation in the matrix. And then we get a translation from matrix. And then we want to use the translation from the end guide. So the end guide. This one, we will take the world matrix and plug it into the translation from matrix. And then we get the translation of the world matrix for this guide. In this case, let's see, because the guide is in world space, we could have also taken the translation of the end guide. But if you, for example, sometimes have a nested hierarchy of guides for some reason, then you should use the translation from a matrix. And because it doesn't really matter for now, we can use the translation. So let's ignore this node because it is in world space. Then we create a 4x4 matrix, and then we're going to ignore this, and we will take the translation x and plug it into the x component of the translation vector, and the y and the z as well. And then we're going to do the matrix add operation. So we need to set everything to 0 except for the translation, because we're adding the values of both matrices together. So add matrix. And then we take the rotation matrix output, and then we take the translation matrix output, and now we have composed the final matrix from the two additions. So again, because we set these values to 0, all of them, they are not getting added. Nothing gets added, and the basis vectors do not get changed. And the 1 value of the W component of the translation vector stays 1 and doesn't become 2. So this way we have a working matrix, which is the oriented end matrix. So this now is the same as our matrix output for the clavicle, and the guide has the same orientation. So let's get the transform. Let's rename this one correctly. So left end out of the clavicle, and then we can take the locator. We can just remove its shape. So if we press down, we will select the shape node. If we then delete, we end with just a transform, just as an empty group. And then we can rename this to be the end guide output. And let's name this respectively. It's world matrix, and this is the let's call this the oriented rotation matrix, and this is the end guide boss world matrix, like so. Okay, now we have created these nodes to construct the guide matrix for this module. And these nodes, again, will only be evaluated on scene load, and thereafter not anymore. So now that we have created our outputs, let's select both of them. Maybe move them somewhere here. Select both the outputs and parent them in the outputs folder of the clavicle. And then we can add them to the tab we're working for the arm. So the arm, we can reroute the parent of the arm module to be the clavicle. So if we now take the offset parent of the end output as a parent matrix, and we plug it into the parent input, then of course the rig will break, because now it's using still the guide from the root, and it's using the current matrix of the clavicle. But as soon as we also swap the guide matrix, take the offset parent matrix of the left end guide of the clavicle and plug it into the guide, then the arm is back at its original correct position. And now if we move the clavicle, we can see that the arm is moving along with the clavicle. In this case it's set to IK. For the FK it will be the same, and this is not the behavior we specifically want for IK, but we're going to fix that with the space switching. So let's finally get to the space switching part. So for this we want to use a few different spaces. For the hand of the IK, for example, we want to be able to set it to the shoulder, to the chest, to the hips, and to the main control. So let's first add an attribute for this. For the FK we are going to use the same. We're going to set the space switch on the settings control. So we create an attribute which is called enum, which is basically a label which are numbered from 0 to 1, 2, 3, and so forth. So we get a enumerated list. So let's set the spaces to be from the most, highest hierarchy to the lowest, so to speak. So we start with the clavicle, and then the next one will be chest. Oh, I should select the text. Chest. And then the third one would be hips without the spaces. And then the fourth one should be main. And then maybe as a last option, we can also do world space. So they are completely locked in absolute world space. So we have clavicle, chest, hip, main, and world space. Let's add this. Maya gives me an error. Must specify an attribute name. Ah, sure, of course. We didn't specify the attribute name. So let's call this space. Okay. So now that we have the attribute, we now have to actually change the spaces of this control. So if we look at the IK control in our IK setup, we get the world matrix for this IK control by multiplying its parent offset matrix that we calculated from the guides with in this case, its parent, which is the clavicle now, because we updated the parents just yet. So now the clavicle is its parent. So we need a way to change the parent without changing its current position, and that's where the node parent matrix comes in. So basically, in the parent matrix node, you have an array of target matrices where you can change the matrix and its relative offset matrix. So let's say add a new item. You have two matrices. The one matrix is the new parent. So if we look at the this one, for example, the target matrix would be the matrix of the parent. So in this case, for example, the output of the clavicle. And then you have an extra option, the offset matrix, which is basically the offset relative to that parent to arrive at the position that it should be. So that is the parent offset matrix. So we have a node which basically does the multiplying of the offset matrix or the buffer matrix with the parent control matrix in one node. So this would be the offset slash buffer matrix, and this is the world matrix of its parent control or parent driver. So we can use this node to switch between all the spaces, and we can weight the target of this space with the weights attribute. So we can drive this with the attribute. So let's set this up now. So the first space that we had defined was the clavicle, which it is already connected to right now. So we can use the matrix that we already multiplied, the buffer with the parent. We can connect that directly into the input matrix. And the input matrix is the only one that does not have a offset and target splits. So that's just the matrix as is, so the matrix in this position that it should be. And only for the targets we specify the offset and the target matrix. So now if we pass this through, so I just put it in between, Maya switches to this position because we have added this target, and it's now switching to two identity matrices. So if we toggle this off, you will see that the arm is at the correct position. And if we remove this target, it's also the same. So it's flipped to the origin because we added the target manually. But now the position does not change, and it still works as before. If we move the clavicle control, the arm moves along with it. So now let's add the chest space. And maybe first call this rename it. Let's take this and we call this IK control clavicle space world matrix, and then we call this the hand IK control world matrix. So now let's move this on. We need to get the output of the chest control, and we need to plug that into an input of the ARM module as well, because we only want connections between the inputs and outputs. And because we're going to have a lot more parent inputs, so to speak, for the clavicle, let's rename this, for the ARM. So let's rename the parent and parent guide, in this case, to clavicle input and clavicle guide input, because these two now connect to the clavicle, and because we're going to get more inputs, it's easier to read if they have the correct name. So let's call this clavicle input and clavicle guide input. And then let's duplicate these and call these the chest input and chest guide input. And let's position these here. Like so. And then we should get the chest outputs of the spine module. So let's go to the spine module, go to the outputs, and we see that we have the chest already because we created these to connect the clavicle module too. So let's add these to the graph. By the way, you can just middle mouse drag them from the outliner to the node editor, and then they are added to the node editor. So we take the offset parent matrix of the chest output and put it into the chest input for this module, and the same for the chest guide. And now we have the chest input. So what we can do for the if we go to the space switching again, here, the parent matrix node, if we again just add the target, if we, for the first target matrix, we can take the output of the chest, and then we can calculate the offset matrix from the guide. So let's take the chest offset parent matrix plug, because that is the driving matrix, and then we go to our node and we plug that into the target matrix. Now of course the hand IK control snaps to the chest position, because that's the matrix of the output of the chest, and as soon as we set the offset matrix or buffer matrix, it will snap back to its position. So we need to calculate the offset of that matrix, so we can do that with another mult matrix node, where we take the input of the IK. So let's see, that is the hand FK, let me see. Yes, the hand FK guide outward matrix. We use that node. You can see as well the hand IK control parent offset matrix for the clavicle space. Also uses this plug, and the world inversion matrix of the clavicle guide. So we're going to take the output of the hand FK guide outward matrix. So it would be maybe better to rename this to be just the hand guide outward matrix, because it's used for both the FK and the IK controls. So let's take this plug and plug it into the first slot of our mult matrix node, and then we want to have this matrix relative to the chest matrix. So we take the chest guide inverse world matrix, plug that in, and now we have created a matrix that brings us from the chest matrix to the hand IK matrix. So if we plug that into the offset matrix of our parent matrix node, you will see that the hand is back to its correct position. And if we now set the weight to 1, you can see that if we change the clavicle, that the IK hand will stay at its position, because now it is following the chest, and as soon as we move the chest, then the hand moves along nicely with it. Now let's rename this note correctly. So let's call this one the chest, let's see, chest space parent offset matrix, or offset matrix we can use as well, because it says offset matrix. But let's leave it at this for now. Okay, so we have incorporated the chest space. So now we can do exactly the same for the hip space. Let's move this down a little bit. So for the hip, we have not yet an output in the spine module. No, so we need to create those first. Let's see which step that was. Oh, I think I just deleted my tab for the clavicle module, I think. But okay, let's see the chest output. So we need to create the hip output as well. So let's duplicate these two, and let's call these hip output and hip guide output. And then we can take the hip control to be the hip output, so the world matrix of the hip control we can plug into the offset parent matrix of the hip output, and we can take the guide, because it is not changed in orientation. We can take the guide for the hips to be the, let's see where it is, the hip guide. We can take that directly, just as with the hip or the chest. We can take that directly to world matrix to plug into the guide output. So let's take the world matrix of the hip guide and plug that directly into the offset parent matrix of the hip guide output. So now we have these outputs as well. Let's take these and add them to the graph of our arm as well. Here, and then we need to create two more inputs for the arm module as well to connect them to. So let's take these, duplicate them, and call these hip input and hip guide input, and then we can connect the offset parent matrices and reroute the plugs. So let's take the offset parent matrix and plug it into the offset parent matrix, like so, for the guide, and then for the hip output as well. We take the offset parent matrix and plug it into the hip input offset parent matrix, like so. And then we can go to the parent matrix, the space switcher for the hand, and we can take the output of the hip and plug it directly into the target matrix for this. So let's take the hip output, so the offset parent matrix, and plug that directly, just like with the chest, plug that directly into the target matrix. So now again the hand changes its position, and because the weights are both on, if we disable this weight completely, you will see that the hand is at the position of the hips, and as soon as we set the correct offset matrix again, it will go to the correct position. So now let's create that offset matrix or buffer matrix. So let's create another mult matrix node. And then again we take the hand guide outworld matrix, because that is the matrix in world space at the hand position, and then we multiply it with the inverse world matrix of the hip, so we get the matrix that gets us from the hip to the hand. So let's take the hip guide output, the offset parent matrix plug, and plug that into our second port. And now we have constructed the offset matrix, parent offset matrix, buffer matrix, however you want to call it, and then plug that into the offset matrix of the parent matrix node. And now you can see I made an error because I took the offset parent matrix and it should have been the inverse world matrix. So let's correct that. Now we have a correct offset matrix. So let's rename this to be the hip space parent offset matrix. So now we as well have a correct hip space. So if we move the clavicle, again the hand stays at its position. If we remove the chest, it will stay at the correct position. And now if we move the hip control, the hand moves along with it. Then we have left the main control space, so we can do the same thing. We already have the main outputs connected to the main inputs. So let's take the main offset parent matrix, and plug that into the next target matrix. And then if we disable the hip weight, then we can see that it's position of the main control. And then again we have to calculate the offset matrix. So let's create another mult matrix node. Again we take the world matrix of the hand guide, and then we take the main guide inverse world matrix, and we plug that into the second plug, and then we take the output input into the offset matrix. And now again we have the correct matrix, where if we move the main control, the hand IK moves along with it. So let's call this one the main space parent offset matrix. And then we have only one left, which was the world space, so it doesn't move along with anything. And for that we can just simply take the world matrix, because the hand world matrix is at this position, so it's basically the offset matrix relative to the world origin. So we can take that and plug it into the offset matrix and leave the driver matrix to be the identity matrix. So if we just take the output matrix and plug it directly into the offset matrix, and then we set the weight for the main to be 0, you will see that now if I move the main control, the hand stays absolutely fixed in world space no matter what I do. So that's the last space as well. So now all that is left is that we have to drive the individual weights of each space to get the space switching to work, driven by the attribute. But because we're not going to blend between these spaces, we're going to hard enable or disable them. So we can as well use the enable target attribute and leave all the weights to 1. So let's do that for now. Let's enable all the weights, set them to 1. And then we can take our settings control, which I apparently hit by accident. We can take the settings control and add it to the graph. Oh, it's already here. So let's move it down here. And then we can use the space attribute and use that to enable the different spaces. So how we can do this is the space attribute is 0 when it's at the clavicle, it's 1 when it's set to chest, and so forth and so forth. So we can just use a simple equal operator to check if it's currently set to the index that is driving for each target matrix, and then if equal is true, then it's 1, so then the wait or the enable is set to true as well. So if we use an equal node and we, for example, plug in the space and put it into input 1, and for the first attribute, so the clavicle, it is index 0, so we need the second attribute to be 0 as well, the second value. And now we can use the output, which is already a Boolean value. We can plug that directly into the clavicle, which we do not have because the clavicle is the first, so we can skip that one. We can set this to 1 to switch for the chest, because the clavicle is the default, so it doesn't have a enable or disable because it's always on, and it will be overridden by the other ones. So if we set it to chest, for example, the input is 1, and now this will result in a true output, so we can take this and plug that into the enable of the chest target. So now you can see this one is overridden, the attribute, because it's grayed out and it's set to true. And if I now, for example, switch to the hip space, you will see that it's disabled. So now it's not using this space. So we can do this for all the different spaces, and we can call this, for example, let's move this down a little bit, put it here, and then we call it just space enable, for example. And now we can duplicate this one and we can call it hip space enable. And we can take the space plug it into this first port, and then we have to set the second value to 2 to match the index of the hip space. And we take the output and plug it into the switcher for the hip, like so. And then let's move this down a little bit. It's going to be a longer list. And then we duplicate this once more, and we call this main space enable. And we set the index to 3 because that's the next one. We take the space attribute again, plug it into the first port, and then we take the output and plug that into the wait for the space. Let's see if it's the correct one. Yep, for the main. So this is the main. And then one last time for the world. Let's call this world space enable. And then we take the space, plug it into the first port, and set the attribute value to 4. And then take the output and plug that into the enable target of the last space. So now all these spaces have been connected, and you can see they're all disabled except for the one that is active. And if I now switch the space, for example, to main, we can see that only the one for the main is enabled and all the others are disabled. So if we now switch to the main, we can see that it moves along with the main control. And if we now switch it to hip, you will see that it moves along with the hip and not with the chest. So this is working. So now we have created the space switch setup for the hand IK control. So the next step is to do the same for the pole vector, because if we want the space to switch for the hand, the pole vector needs to switch along with it, because if we, for example, now orient or set the space to the chest or hip, and if we now move the clavicle, you can see that the pole vector still rotates with the clavicle, which is not what we want. We want it also to be in the same space. So we're going to use the same attribute to drive the spaces for the pole vector or the elbow IK control as well. So for this we're going to do the same setup basically. So let's go to the elbow control, and here's its world matrix, and for this we are using a blend matrix to blend to the specific position. So for this we are using the output of the hand as the position. So let's move this down here. Like so, and then we have our IK elbow world matrix and its paired offset matrix. So again, this is the equivalent of this one, like the hand IK parent offset matrix and the hand IK clavicle space, as we renamed it. That's basically the same as this, the offset matrix for the guide and the base world matrix. So let's introduce our parent matrix here, parent matrix node, and plug the world matrix into the input matrix. And then take the output and reroute it to the position blending for the control. Like this. Remember this control sets the position of the elbow to the desired position that we want in the rig. Okay, so now that we have this, let's call this in the same manner, world matrix, so we call it. So we already have used the name base world matrix, so let's call this maybe space switch world matrix. Okay, and this was then the let's create the same name. Okay, and then we can maybe just call this base world matrix again to keep it consistent. As you see, I change my mind sometimes as well. Oh. And now let's add the other spaces to this. So now the basis space is the clavicle again, so we need to add the chest. So let's add a melt matrix node to get the chest offset matrix. And then we're going to use the same base matrix as we used for the clavicle. So that is the oriented plane guide, which is the matrix that is the orientation of the arm pointing towards the hand and oriented with the upper guide to orient the orientation plane, which was the basis for the control, the elbow control. So let's take that world matrix and plug it in here. So now we have the guide, the base position of this guide. So if we set the blending, sorry, it's on the switch on the settings control. If we set the blend pos for the elbow to 0, it's basically this matrix, the guide matrix at this position, and afterwards we're going to blend it with the blend matrix node. So it's this matrix that we have plugged in here, and now we can multiply it with the inverser world matrix of the chest guide, so we get the offset from the chest guide to this guide orientation. So let's take the, let's see what it is, the chest, and then the chest guide world inverser matrix. Plug that in. So now we have the offset matrix. And let's see how we call that here. Chest space parent offset matrix. So, and then for the elbow IK, like so, I think. Yes. All right, to keep it some consistency in there. So now we have the offset matrix, so we can expand the first target, and as a driver we need to have the chest input world matrix. So we take the chest input and take its offset parent matrix, which connects to the output of the chest module for the or the spine module and the chest control. And then we plug that into the target matrix, and now you will see that the orientation is wrong and the position is wrong, but as soon as we plug in the offset matrix, then it's back to the correct orientation and position. So this is the chest space. So let's duplicate this and then call this the hip space, parent offset matrix. And again, let's take the same guide world matrix for its base position and orientation, and then multiply it with the world inverser of the hip input. So let's go to the hip guide and take the world inverser matrix, plug it into the second. So now we have created the offset matrix, and now in the second target we can plug the hip input. So the hip input offset parent matrix, and we plug that into the target matrix, and now again we can see that the orientation is wrong, and if we disable the target, the first target, you can see that it's at the position and orientation of the hip control. And now if we plug in the offset matrix, again we go back to the correct orientation. If we disable this target, nothing changes. Okay, then we can do the main. So again, duplicate this node and rename this to main space parent offset matrix. And then again we take the same guide matrix, oriented guide matrix, as the basis, and then we take the main input. So we are main guide world inverser matrix. Now we have the offset matrix, and then we can plug in the main input matrix. So the offset parent matrix plug from the main input, plug that into the target matrix, and then again we can see that the elbow control orients to the main control, and as soon as we plug in the offset matrix, it returns to its correct orientation. And then as a last space, the absolute world space, we can take the guide matrix again and plug that into the offset matrix, and leave the matrix, the target matrix, to be the identity matrix. Okay, so these are the space switches for this, and now we can use the same attribute and the same enablers basically to drive the space for this. Because we're using the same attribute, the enablers are the same. So we can take the chest enabler and plug that into the chest enable attribute, and the same for the hip. We can plug it into the hip and the main into the main, and the world into the world. So now the enablers are driving both the IK hand and the IK elbow control. So let's maybe separate them out. Align these like so, and this like so, and then we have the enablers in the middle. Okay, and now we can set back the blend, because we don't need the visual cue anymore. So let's maybe set it here. And now if we set the space for the switch to clavicle, then we can see that both the IK control and the elbow, the hand control and the elbow control move along. And if we switch it to the chest and we now move the clavicle, then they both stay fixed to the chest. And if you now move the chest, they move along, and if we rotate the chest, they orient nicely with the chest control, and so forth and so forth. If we change it to the main, then we can rotate any control down here, but they will stay in their place. And the only thing we need to fix now is that because we locked the position, the base position of the elbow control is now a child of the main control. If you now rotate the hip, or the center of mass control in this case, the position of the elbow control does not change, and you would expect it to still blend between the start position of the arm and the hand position of the IK, but now it stays locked in place. So if we, for an extreme case, would move this away, the control stays behind in space, but we want it to be in between these positions. So we need to fix that first. So we can do this by adding another entry to our blend matrix node, because now we are blending from the current position of the IK control. So if we set this value to 0, this position, if we now, for example, move away the center of mass control, you see that it stays at this position, and then it blends to the position of the hand with the blend matrix here. So what we need to do is we need to fix the initial position. So what we can do is we can add another target that first blends the position to this position, and then from this position blends to the hand by the amount that we want via the settings node. So to do this, and because we're using only the translation, it's relatively cheap to use the blend matrix node, so we can just keep using this. So we need to shift the first target 2 into the second target. So let's do this, plug this, and take the target matrix and plug it into the target matrix. And now we need to get this position that is already correctly moving along with the parent control and plug that into the first target matrix, and then 100% blend to the to this matrix. So let's break this connection. Of course, Maya doesn't work this way. Let's first plug in the matrix and then move the connection, because as soon as you remove the connection, then Maya deletes the first target because it has no connections to it. It's a default behavior for this node, unfortunately. So the matrix that gets us to this position is basically the FK control driver matrix. So if we have the upper FK guide outward matrix, which then is calculated its relative offset or its parent offset matrix or buffer matrix, and then and it's calculated relative to the parent, which is now the clavicle, and it is then multiplied with the out clavicle, it produces the world matrix that is the basis for the FK control. And this matrix is the matrix that's always at the start of the arm, no matter the space switching. So we're going to use this matrix to blend the position 2, because the position is always at this start of the arm. So let's take the output of this and then plug that into the target matrix of the blend matrix. Then remove the connection. And now if we set this to, for only the translation, to weight of 1, we can see that now the control, the elbow control, is moving along. So if we now move this, the elbow control is now moving along. And because we are now blending in the second input of this blend matrix the position of the hand, and then because we reconnected to the second port, these values are not correct, so we do not want to scale the rotate and the shear, we only want to translate as well. And it is driven by the attribute on the settings control. So if we now slide the blend control, the elbow control nicely blends between the start of the arm and the hand IK control, no matter how the space switching is set and where the rest of the rig is moving towards. And even if we rotate this, it still keeps working. So now we can reset this, and we have a functional space switch for the IK part of the arm. So now we have to set the same thing up for the FK part of the arm. And for the FK, we only want to switch the rotation space, so to speak. We do not want to switch the translation, because the translation of the FK arm should always be attached to the clavicle, no matter what the space switch is set to. So we're only going to switch the rotation for this control. So if we look at this control right here, so we have the parent offset matrix and its world matrix that plug into the input of the FK control. And now we are going to set up the same kind of space switching as we did for the IK control. So let's add the parent matrix node, like so, and then plug in the world matrix into the input matrix, and then we take the output matrix and plug it into the offset parent matrix. And now we have inserted the node without changing anything in the rig. And let's rename this correctly. So let's call this the clavicle space world matrix, and this the out world matrix. And then we do the same thing. We calculate the offset matrices for each space. So let's start with the chest again. So let's create a node matrix node, and we take the oriented guide for the FK control. So this matrix, which is basically the matrix that is at this position and oriented according to the rotation plane of the arm. And then we multiply that with the inverse world matrix of the chest guide. So let's go to the chest guide input and take the world inverse matrix plug and plug that into the second port. So now we have calculated the offset. Let's see how we call this again. Chest space parent offset matrix. So let's call this chest space parent offset matrix. Okay, and now we can take the chest output or chest input matrix, so the chest input offset parent matrix plug, and plug that into the target matrix. And now again we can see that the FK control swaps or changes position to the position of the chest. And now if we take the output and plug it into the offset matrix of the chest space parent offset matrix, the control returns to its correct position. And then we can go to the second space. So let's duplicate this one, maybe move this up a little bit to create some space here. And let's call this hip space, parent offset matrix. And again, we're going to use the same basis matrix, the oriented guide world matrix, and multiply it in this case with the hip input guide inversion world matrix. So the hip guide input world inversion matrix, and we plug that, where are we here, into the second port. Now we have our offset matrix or buffer matrix, and then we can take the hip input world matrix, so the hip input offset parent matrix, plug that into the target matrix, and then we can see that if we disable the first target, that we are completely switched to the position of the hip and the rotation of the hip. And if we now plug in the offset matrix that we calculated into the offset matrix, it will return to the correct position again. So that's correct as well. Then let's do that again for the main control. So let's take the guide of the upper FK, let's call this main space, and then we take the inversion of the main input guide, so the main guide input in the world inversion matrix, plug it into the second port, and then again we have the offset matrix. And if we now take the main input matrix, so the main input, and then the offset parent matrix plug that into the target matrix, and we disable the hip target, we can see that the control indeed switches to the main control. And if we then plug the offset matrix in again, we are at the correct position and rotation. And then as a last step as well, we duplicate it again and then create the world space, parent offset matrix. So we take the oriented guide world matrix and multiply it with the we don't need to multiply it. We can take the oriented guide world matrix and plug it directly into the offset matrix. So we do not need this node. So it's the same as with the other space switching. We just use the oriented guide directly in the offset matrix. Okay, so now we have set up the space switching, and then we can use the same enablers to drive, because we're going to use the same spaces for the FK and the IK. So let's see, this is the chest enabler, so let's plug that into the chest enable target, and the hip into the hip, and then the main into the main, and then the world into the world. And then we can move these back down here like so. And now we have created this space switching. However, we did not compensate for the translation we want to ignore. So if we set the space to chest, for example, and if we now move the clavicle control, we can see that the FK control stays at its position relative to the chest, but we do want to move it with the end of the clavicle. We only want to maintain its orientation. So we have to do the same kind of trick as we did for the IK elbow control, we need to blend the position of this to be always the position of the original input for the clavicle space, so to speak. So if we take the clavicle space, this one is always the one with the right translation. If we make a temporary locator, for example, we can see that if we plug that in here, this is the position that we want to use regardless of the space that we're in. So we can do the same trick as before. We can use a blend matrix node, and then we can plug in the output of the space switching node, and then we can take the clavicle space world matrix as a target matrix, and then we can disable the scale, rotate and shear, and only set the translate weight to 100%, so to 1. And if we now reroute the output to the output of this node, we can see that the FK nicely moves along with the clavicle, but it maintains the orientation relative to the chest control. So only if we rotate the chest control, the FK rotation is taken into account. And again, if we, for example, set the space, reset the translation of the clavicle. If we now set the space to be hip, for example, if we now rotate the chest, the translation is taken over from the clavicle, but the orientation is not changed of the FK. Let's maybe switch to FK for better visuals. You can see that the arm is moving along, but the orientation is not changing. The orientation is only changing with the hip control. And because the IK control of the chest is independent of the hip, for the FK it's kind of a weird setup this way, but you could do this. You could have the arm rotate with the hip while the chest stays, doesn't rotate with it. So okay, so this is the space switching. So let's reset all these controls to their default values. Like so, this as well. And then switch this to chest, for example. As an alternative to the blend matrix, we could also use the row from matrix nodes. So we need 4 row from matrix nodes, 3 for the output of the space switching, so we get the basis vectors x, y, and z, and 1 for the clavicle space world matrix, so we get the translation vector, and then we can port the output directly into a 4x4 matrix, skipping any multiplications. But because we're only using the translation, my assumption is that Maya does not do any doesn't do a lot of multiplication. It's only blending the translation. So it's getting the translation from the matrices, blending that and setting that back into the matrix. So I'm not 100% sure, but I think that in the end, for this setup, the speed benefit is small to none. So we can maintain the blend matrix node. So let's rename this now. So I renamed the blend node to be the control world matrix, and I renamed the parent matrix node to be the rot world matrix. So the rotation, because we're only using the rotation matrix. So the 3x3 part with which has the rotation, scale, and shear in it, and we're taking the translation from the clavicle space matrix. So we can remove the temporary locator, and we have finished our space switching setup. And there's one thing we always have to do in the end to check if everything works, and that is to scale the rig and see if all the spaces still work when we are scaling. So let's do some rotation and see if this works. And if we put it to clavicle, the arm IK, FK nicely orients along. Yep. And if we enable log length, we can see that the rotation of the arm is nicely following the clavicle rotation. So disable this again, set to 0, and everything seems to be working just fine. So we can call it a wrap.